Hello everyone, welcome back once again. This is BB Sangmay, and today in this lecture I am going to discuss about the principal stresses and principal planes. Okay, in the second videos of this chapter, that is unit 2, design of machine element against static loading, we have discussed about the various types of stresses acting on the machine component. Okay, so first of all, here I'm going to discuss about the types of loading. So here I have taken one component on which I am going to apply a force of magnitude P along the x-axis, okay, which is having a tensile nature. So as we know that when a force is applied on the component, an internal resisting force will get induced inside the component. So that internal resisting force is nothing but stress. So as here in this case I have applied a tensile type of force, there will be a stress which is called as a sigma x. It is nothing but the tensile stress, which is the internal resisting force which will get induced after the application of force P. Okay, so if I will divide the value of applied force P by the cross-sectional area of the component or the area under tension, then that force, the formula will be, it will be P by A, and P by A is nothing but actually it is the stress. Okay, so that will be the tensile stress. So I can reconstruct the same figure in this manner. Okay, so when we will apply an external force, there will be internal resisting force which is called as a stress. So sigma x is the internal resisting force which will act, which is actually acting along the x-axis. Okay, so to this particular type we can call it as uniaxial loading, and the same principle or the same thing happen in case of a tensile testing of the component, which is also tested in uniaxial manner. Okay, so this is called as a uniaxial loading. When I will apply a force in x direction, there will be a stress in x direction, and similarly simultaneously when I apply a force in y direction, there will be a stress in y direction which is called as a sigma y. So here you can see that sigma x, it acts along the x-axis, and sigma y, it acts along the y-axis. These are the two stresses which are getting induced after the application of force. So this type of system or this type of stresses or this type of loading is called as a biaxial loading. Similarly, when a component is subjected to, when a force or when the component is subjected to a force which acts along x direction, there will be a stress which is called as a sigma x, which will be get induced along the x-axis. So simultaneously when there will be a force along y direction, there will be a stress which will get induced along the y-axis, which is called as a sigma y. And when there will be a force along the z-axis also, simultaneously there will be a stress which will act along the z-axis. So this is the case of triaxial state of stress. Okay, or you can call it as a triaxial loading. Okay, so here you can see that while testing the properties of the material, we usually go for the tensile testing. Okay, where the component is subjected to uniaxial type of loading. Okay, and by doing this we get the values of SYT, that is yield strength in tension, and SUT, that is ultimate tensile strength of the material. Okay, but in actual practice we cannot predict that the component will only get subjected to uniaxial type of load. It can get subjected to biaxial type of loading, it can get subjected to triaxial type of loading. Okay, so we are going to see that what exactly happens or how the stresses inside the component can be calculated when the component is subjected to biaxial or triaxial type of loading. Okay, so before that, going for the discussion of principal stresses, I'm going to discuss about the principal planes. Okay, the principal planes, it is important to know what are the how the principal plane is identified. Okay, so here principal plane, it is the plane on which only normal stresses will act no shear stress will act on the on that plane. So here once again I have recreated the image. Okay, so here you can see that the component is subjected to, this is the case of biaxial loading. Okay, the load is applied along x-axis and y-axis, that is why the stress is acting along the x-axis and y-axis. Okay, so here you can see that as I have given the definition of principal plane, it is the plane on which only normal stresses will act, no shear stress will act on that plane. That plane will be called as a principal plane. So here you can see that sigma x is acting on this face and also on this face. So these two planes can be called as the principal planes. Okay, and also sigma y, which is the stress because of the tensile force in y direction. Okay, so here you can see that both the stresses sigma x and sigma y are acting normal, that is perpendicular to the area. Okay, so these vertical faces of this particular component and the horizontal faces of the particular component can be called as a principal planes, because on this all faces there is no any kind of shear stress. Okay, so as according to the definition, it is the plane on which only normal stresses will be there. Okay, so these are the all four planes are having normal stresses. Okay, which are acting perpendicular to the area. Okay, so these all four faces can be called as a principal planes. Okay, so what happens, so here what I am going to do, I am going to discretize, or I am going to divide the same component into small number of components. Okay, so you can see that I have divided the total component into small elements. Okay, so these total area of the particular plane or the component is divided into a finite number of elements. So I am going to consider a single element. So when you will apply a force in a tensile manner, here you can see that the stress is acting, biaxial type of stress or biaxial type of loading is there. When you will apply a force of magnitude P, okay, or when you apply a stress along x-axis and along y-axis, a single element inside this complete component will also, it is also subjected to same type of stresses. Here I will give the example. You have to consider the first element. When I will apply a force along x-axis, there will be a stress along x-axis. So similarly and simultaneously when I will apply a force along y-axis, there will be a stress along y-axis. So every element, every single element of this which is inside the component will be subjected to the stress of same magnitude sigma x and sigma y. Okay, so here I am going to take the enlarged image of this element. Okay, so you can see that single element will be subjected to of the total component will be subjected to same type of stress sigma x and sigma y. Okay, generally principal stresses are represented as sigma 1 and sigma 2. Okay, so here in this figure I have considered one element. Okay, so here once again let me remind you that the principal planes are the planes on which only a normal stress will be there. There will not be any kind of shear stress acting on those planes. Okay, so here you can see that the vertical plane of this element, the vertical sides of this element are subjected to normal, that is the load which acts perpendicular or the stress which acts perpendicular. So these two vertical faces are, let me highlight this. Okay, these two vertical faces are actually, these are the principal planes. Also here you can see that the horizontal faces are also subjected to tensile type of load only. Actually the load is actually acting exactly perpendicular. Okay, here you can see that. So these two planes are also can be considered as a principal planes. Okay, so generally principal stresses are represented as sigma 1 and sigma 2. So here you can see that the sigma x is having some sort of a larger magnitude as comparatively sigma y. Okay, so here I am going to consider as a sigma x as a major principal stress and sigma y as the minor principal stress. As we have discussed that the stresses which act perpendicular or normal to the plane, these planes are called as a principal planes, and these stresses are called as a principal stresses. So here actually principal stresses are represented as sigma 1 and sigma 2. So I can write this equation as a sigma 1 is equals to sigma x and sigma 2 is equals to sigma y. So sigma x is the major principal stress, okay, because sigma x is greater than sigma y. Here I have assumed that sigma x is greater than sigma y, and sigma y is, as the sigma y is less than sigma x, so sigma y is the minor principal stress. So we can call it as a sigma 1 is the major principal stress and sigma 2 is the minor principal stress, or we can call it as it is the maximum principal stress and is the minimum principal stress. Okay, now here I have recreated the same element, okay, on which I am going to apply an axial force along the x-axis, which is going to induce a stress along the x-axis, which is called as sigma x. Similarly, I am going to apply a force along the y-axis, which is going to induce a stress along the y-axis, which is called as a sigma y. So here in this figure, in the previous one, we have not considered any kind of shear stress. In this element, I am going to consider a shear stress. Okay, so here you can see that I have applied a shear stress along positive x-axis, but the shear stress is acting over the y area, so that is why it is represented as tau yx. So this stress is acting towards the positive x-axis, as we know that the compressive and tensile stresses acts perpendicular or normal to the area, but shear stress is the only stress which acts tangent to area. Okay, it acts over the area. So this is the shear stress which acts on the upper side of this element. So actually the stress is acting towards the positive x-axis, so this x represents the direction of stress and y is the area over which the shear stress acting. Similarly here tau yx is actually representing, here x is representing the negative side, here actually the tau x is actually acting towards the left side, okay, and y is again representing the area over which the stress is acting, or the area to tangent to the area to which the stress is acting tangentially, shear stress is acting tangentially. Okay, so here similarly here you can see that these two stresses are actually creating a clockwise couple. They are trying to rotate the element in a clockwise direction. So I'm going to apply two more stresses, those are also actually, these are also shear stresses. Here tau xy, this is the stress which is actually acting in the downward direction, which is, it is acting towards the negative y direction. Okay, so x is actually the area over which it is acting and y is the direction. Okay, similarly tau xy, here x is the area over which or to which the stress is tangent, and the y is the direction, the stress is actually acting towards the positive y direction. So here in this case you can see that I have applied a tangential force along x-axis which is inducing the tensile stress. I have applied the tangential force, not tangential force, sorry, I have applied the axial force along the x-axis which is inducing the axial tensile stress, which is called as a sigma x. I have applied the axial tensile force along the y-axis which is representing the sigma y. Okay, so here let me tell you that the tensile stress is considered as a positive and compressive stress is considered as a negative. Okay, so here let me tell you one thing, that the magnitude of tau x and tau xy is same. So here you can consider that tau xy is equals to tau x or vice versa. Okay, so here in this figure it is little bit different than the previous one. In the previous one actually the component was subjected to the biaxial state of stress, but there was not any kind of shear stress. But in this figure you can see that there is a shear stress. As I have already told you that the principal planes or the principal stresses, let us first discuss about the principal planes. As I have already told you that the principal planes are the planes on which only axial tensile type of force should be there. Okay, there should not be any kind of shear stress. Okay, only tangent, you can call it as a normal stress will be there, as I have already said, given the definition of the principal plane. On the principal plane only normal type of load will act. If on any plane there will be a shear stress, then that plane cannot be called as a principal plane. Okay, so here in this figure you can see that the two vertical sides of the element are subjected to normal load, that is normal stress sigma x, and also they are subjected to shear stress. So these two vertical sides cannot be called as a principal planes, and also sigma x cannot be called as a principal stress. Okay, similarly, if you take the topmost horizontal plane and bottommost horizontal plane of this element, okay, so on this topmost side there is a stress which is acting normally, okay, which is perpendicular, but there is also a shear stress. There is also shear stress at the bottom of the plane. Okay, so these two planes also cannot be called as a principal planes, because on these two planes there is a shear stress. So sigma y also cannot be called as a principal stress. Okay, so do remember one thing, that the principal planes are the planes, are those planes on which only a normal stress should be there, a normal type of force should be there. Okay, so sigma x and sigma y cannot be considered as a principal stresses, and these all four walls of this plane, or you can call it as all four sides of this rectangle, cannot be called as a principal planes, because on all the four sides there is a shear stress also. Okay, then where is actually the principal plane? So what I am going to do, I am going to draw a plane inside the element, okay, which is inclined at an angle of alpha. Okay, so on this plane, if you see on this plane, whatever the applied force for the application of force in x direction, actually the stress is sigma x. So if you extend these two lines, here you can see that it is not actually normal to the plane. So okay, and also if you see the stress which is acting in y direction, it is also not perpendicular to this inclined plane. Okay, so here also, as I have said, that the whatever the normal stress sigma x sigma y acting on these four sides of the element, and whatever the tau xy and tau yx, which are actually having equal magnitude, these are acting on the surface of this particular element. Okay, so this is, I am going to consider this, I have drawn here one line which is inclined at an angle of alpha. Okay, so on this line I am going to draw an element which is actually having the orientation like the plane, along the plane, as we have seen that here the sigma x and sigma y both are actually perpendicular or normal to these sides. Okay, so let me show you. Here you can see that sigma x is actually perpendicular to the vertical side, okay, and sigma y is actually perpendicular to the horizontal side of the element. Okay, but here as I have already said in the previous slide, the actual component is, I have discretized, or I have divided the actual component into small elements. Okay, so here I am going to consider one element. Here you can see that this is the element which is actually inclined, which is having the orientation along this inclined plane. Okay, so when you apply a force along the x and y direction, there will be a stress, but on this particular plane there will be this particular element, smaller element, you can see that there will be a stress in this manner. Okay, as here you can see that the stress is actually applied force, principal stresses are actually acting normal to the area, but we have to neglect the shear stress. Okay, but in this particular smaller element which is inside this larger element, on this element there will be only a principal stresses, there will not be any kind of shear stress, okay, which will act in along the axis like sigma 1, as I already said that the sigma 1 is equals to sigma x, and there will be a stress along the y axis or along this plane, inclined plane. It can be called as a sigma 2. So here sigma 1 and sigma 2, actually these values or these particular stresses can be called as a principal stresses. Then why these are called as a principal stresses? Because here on this particular element, whatever the stresses are acting, sigma 1 is the major principal stress and sigma 2 is the minor principal stress. Here you can see that the sigma 1 is actually perpendicular to this wall of the element, and sigma 2 is also perpendicular to this wall of or this side of this particular rectangular element. Okay, so here you can call it as sigma 1 can be called as a major principal stress and sigma 2 can be called as a minor principal stress. Okay, now here I'm going to draw an element like, so consider this element like the total component, okay, which is subjected to a triaxial loading. Okay, so here on this element there will be a stress, and along x-axis it will be sigma x. Okay, there will be a stress along y-axis, it will be sigma y. Okay, so here you can see that the whatever the magnitude of sigma x and sigma y acting on this element, that will not be similar to the magnitude of sigma 1 and sigma 2, those who are acting on this element which is along this inclined plane, which is the principal plane. Why this is the principal, this is called as a principal plane? Because on this element here you can see that as there is a normal stress sigma x and sigma y acts, also there is a shear stress tau xy and tau yx acts along the surface of the element. Okay, so the magnitude of sigma x which is acting on this element, which is having the orientation like the actual component. Okay, so here this is having the orientation like the actual component, but the element which is actually having some inclination along with the vertical side. Okay, if you reduce the alpha, it will make the alpha 0. Okay, for the value of alpha is equals to 0, this element will be, it will look exactly like this, and it will be only subjected to sigma x and sigma y and tau xy and tau yx also. But in that case sigma x and sigma y will act exactly normal to the vertical and horizontal faces of the element. But in this case you can see that sigma 1 is the major principal stress and sigma 2 is the minor principal stress, and this is called as the principal plane, because along these planes only the normal stresses are there. So as I have said that sigma 1 is the maximum principal stress, there is a possibility of failure of this total element along this plane, along this principal plane. Now the question is, why we are studying these principal stresses? Or because in actual practice the components are subjected to biaxial or triaxial type of loading. Okay, so let us take the example of the brittle material. As we know that the brittle material are strong in shear. Okay, so we need to focus on the failure of the brittle material in along the principal stresses or along the principal planes. Okay, so you can see that if suppose this material is the brittle material, this component is made up of brittle material, then as I have said that the maximum principal stress will be sigma 1 after the application of force of sigma x, sigma y and tau xy and tau yx. After the application of these all stresses, the maximum principal stress will be sigma 1 and it will act along this direction, and as we have seen that it is acting actually in a tensile manner, and we know that the materials which are brittle are having negligible yield strength. Okay, so there is a possibility of failure of the brittle material in tension. So for the case of brittle material we need to consider the sigma 1, the value of sigma 1. Okay, and as we know that there will not be any kind of, as we have neglected here shear. Why we have neglected shear here? Because the brittle materials are strong in shear, so we need to focus on the where the material is exactly weaker, and we know that the brittle materials are weak in yielding. Okay, so there is a possibility of failure of brittle material in a tensile manner. Okay, because they don't have any kind of yield strength. So when a force will be applied on the whole element, okay, when there will be a force where there will be a load or stress along x-axis, y-axis and the shear stress. The failure of the brittle material, it will take place along this inclined plane. So that is why it is called as a principal plane, because along this plane these two stresses, that is sigma 1, and actually sigma 1 is normal perpendicular to the principal plane. Okay, so it is the maximum principal stress, and the failure of the material or particularly failure of the brittle material, it will take place along this plane. Okay, now here we have seen that for the case of brittle material, the component will fail along this plane because of the maximum principal stress, that is sigma 1. Why? Because brittle materials are weak in tension, they don't have any kind of yielding. Okay, now the question is that why we have not considered any kind of shear stress inside this component, inside this element. Okay, we have only considered the principal stresses which are acting normal to the element. Okay, so here I am going to explain that when we are going to consider the shear stress. Okay, so here I am going to redraw this figure. Okay, so here I am going to draw the same element on which there will be a tensile stress sigma x, or there is a normal stress. Okay, and also a stress along y-axis. So in this element I am going to draw a plane which is inclined at an angle of 45 degree. Okay, so here in this figure I am also going to draw the same plane which is inclined at an angle of 45 degree. Okay, so here it will look like this, and this angle will be exactly 45 degree. Okay, this is also 45 degree, and if you consider the element, if will increase the inclination of this plane, if you will incline this particular line at an angle of 45 degree, the element, the position of element will be like this. Okay, and for the angle of 45 degree, which is the maximum one, okay, the shear stress will be maximum, which will act along this side in this manner. Okay, and for the application of force sigma x, sigma y, okay, and tau, there is a possibility of failure of the material along this plane, which is called as a principal plane, along which the shear stress will be maximum, that is tau max. Okay, so here as we know that the ductile materials, the materials which are having the yield point, maximum yielding, they are weak in shear. Okay, so in case of ductile material, we have to design the components according to the maximum shear stress theory, or according to the maximum shear stress, that is tau max. So we need to calculate the value of tau max at an angle of 45 degree, because at the angle of 45 degree the shear stress will be maximum. Okay, and when we will go for the design of brittle materials, we need to consider the sigma 1, because for the value of sigma 1 the shear stress, sorry, the principal stress, sigma 1 is actually maximum principal stress, and the brittle materials are weak in tension. Okay, so while designing the brittle materials, we need to consider the maximum principal stress, that is sigma 1, and while designing the ductile materials, we need to consider the maximum shear stress, tau max. Okay, in the next video I am going to discuss about the Mohr circle, and we are going to see how the values of sigma 1 and sigma 2 and tau max can be calculated by using Mohr circle. Okay, thank you.